Many multivariate statistical analysis procedures are based on an assumption that the responses have a multivariate normal distribution. Multivariate normal distributions have a number of parameters, and research questions are framed in terms of those parameters. Answering these research questions is not as simple as observing the values of the parameters or making mathematical comparisons among them, because the true values of these parameters are unknown in any real-world situation. Rather, statistical inference must be used in answering these questions. This involves estimating the various parameters of the multivariate normal distribution from data, testing hypotheses about the parameters, and constructing confidence intervals for individual parameters and confidence regions for sets of parameters. In this lecture video, we're going to use the maximum likelihood principle to derive estimators for normal distributions. We're going to do this for the univariate normal distribution as well as for the multivariate normal distribution. We'll begin by deriving estimators for the two parameters in the univariate normal distribution, the mean and the variance. We'll start here because from our previous statistics courses, we're already familiar with the univariate normal distribution and the estimators of its parameters. Another reason we'll start here is because it's mathematically easier to present notationally, to discuss, and to understand. Once we become familiar with the process for deriving the estimators for the univariate case, we'll take what we've learned and proceed, by analogy so to speak, into a discussion of the derivation process for the multivariate case. Whenever learning something new, it's always a good idea to try to connect it with what we already know whenever possible. With that in mind, we start off our development with what we are already familiar with, the univariate normal distribution, and we derive estimators for its parameters. We will see that these are the estimators we're already familiar with from our previous studies in statistics. We define and construct the likelihood function, which is the starting point for our derivations. We then talk about the big idea behind a maximum likelihood estimation from a conceptual standpoint. After we've done that, we dive into a detailed and complete derivation of the maximum likelihood parameter estimators. Now, we usually want our estimators to be unbiased, and so once we've obtained the MLEs through this derivation process, we evaluate them from the standpoint of bias and make adjustments where necessary. We then move on to the general multivariate normal distribution and a derivation of its many parameters. As before, the starting point is the likelihood function, and we define and construct it for the multivariate normal case. We again discuss maximum likelihood estimation, this time for the multivariate normal distribution, and we find that the only real difference between that and the univariate normal case is the dimensionality of the parameter space. We then set up and discuss the derivation process. Because for the multivariate normal, we are now working with vectors and matrices of parameters rather than scalars, the mathematics are a bit more involved, and so we don't show the derivation details, but we proceed by and rely upon analogy with the univariate normal derivation to provide solid conceptual understanding. We find that the estimators obtained for the parameters of the multivariate normal are natural generalizations of the estimators obtained for the univariate normal. Finally, we evaluate these maximum likelihood estimators from the standpoint of bias and make adjustments where necessary. So we've got a lot to do. Let's get to it. In this first major section, we look in detail at the process for deriving parameter estimators for the univariate normal distribution using maximum likelihood. The starting point for our derivations is the likelihood function, which we need to define and construct. Let x1, x2, and so forth up to x sub n be a random sample of size n from the normal distribution with mean mu sub x and variance sigma squared sub x. Now let me first say that because it's a random sample, the random variables comprising the sample are stochastically independent and identically distributed. In other words, they are IID. So we could have equivalently said, let x1, x2, and so forth up to xn be IID random variables from the normal distribution with mean mu sub x and variance sigma squared sub x. For each I going from 1 up to n, the marginal PDF of the ith random variable x sub I is given by the following. Now note first that the marginal PDF for the ith random variable is subscripted with I, and so f sub I is the marginal PDF of x sub I. The PDF is given by 1 over the square root of 2 times pi times sigma squared sub x times the exponential function evaluated at -1/2 times the ratio of the square of the difference between the argument little x sub I minus the mean u sub x divided by the variance sigma squared sub x. Now notice that all of the x sub i's have the same expression for the PDF, the only difference being the argument x sub I. This reflects the fact that they are identically distributed. Now, because the random variables comprising the sample are stochastically independent, their joint PDF is equal to the product of their marginal PDFs. The joint PDF is denoted by lowercase f, which you'll notice is not subscripted. So we're using lowercase f for the joint PDF, and we're also using lowercase f for the marginal PDFs. But in order to distinguish between the joint PDF and the individual marginal PDFs, we've subscripted the marginals with I. And so that helps us to differentiate between these various functions in this construction. So again, because the random variables are stochastically independent, their joint PDF is equal to the product of their marginal PDFs. This fact allows us to construct the joint PDF very easily. And so when we carry out that multiplication, we get the expression on the right-hand side. Now, if the random variables were not stochastically independent, then this equality would not be true. In other words, the joint PDF would not be equal to the product of the marginals. And if it's not equal to the product of the marginals, then we really would not have any idea what that joint PDF would look like. Because of this, independence of the random variables is crucial. If they are not independent, then nothing that we're going to do following this is applicable, because all that follows is based on dependence. Now we think of this joint PDF as a function of the variables x1 through xn given fixed values of the parameters mu sub x and sigma squared sub x. This is reflected in the notation, specifically in the argument list, how we list those arguments to the function. We have x1 through xn before the semicolon, and so they are considered as variables. And then after the semicolon, which by the way we read as given, we have the two parameters mu sub x and sigma squared sub x. So when we think about this joint PDF, we're considering x1 through xn as being values that vary, and the parameters mu sub x and sigma squared sub x as being fixed constants. So again, we think of the joint PDF as a function of the data, little x1 through little xn, given fixed, albeit unknown, values of the parameters mu sub x and sigma squared sub x. The likelihood function reverses this interpretation. The likelihood function is just the joint PDF, considered as a function of the parameters mu sub x and sigma squared sub x, given the observed values of the data x1 through xn. So in working with the likelihood function, we think of the variables x1 through xn as being fixed and allow the parameters mu sub x and sigma squared sub x to vary over the parameter space. The expression for the likelihood function is therefore equal to the expression for the joint PDF, and we just consider it to be a function of the two parameters mu sub x and sigma squared sub x. Recall that the parameter space of the univariate normal distribution is the set of ordered pairs mu sub x and sigma squared sub x, where mu sub x can be any real number, but sigma squared sub x, the variance, has got to be a positive real number. Graphically, the parameter space is that part of the two-dimensional Euclidean plane above the horizontal axis, which is the shaded region in this graph. The horizontal axis corresponds to mu sub x, and the vertical axis corresponds to sigma squared sub x. The mean mu sub x can take on any real number, negative, 0, or positive. The variance, sigma squared, on the other hand, must be positive. Before we dive into the mathematical details of the derivation process, let's talk about the conceptual idea underlying maximum likelihood estimation. If there is a point in the parameter space such that the likelihood function at that point is greater than or equal to the value it takes on at every other point in the parameter space, then that point at which it attains its maximum is called a maximum likelihood estimator, or MLE, of the true parameter point. Expressed notationally, if there exists a point mu tilde sub x and sigma tilde squared sub x in the parameter space, such that the likelihood function, denoted by uppercase L, evaluated at that point is greater than or equal to the likelihood function evaluated at any other point in the parameter space, then that point, mu tilde x, sigma tilde squared sub x, is called a maximum likelihood estimator of the true parameter point. Therefore, to find maximum likelihood estimators of the parameters, we must find values of the parameters in the parameter space which maximize the likelihood function. Now this raises a few important questions. Do maximum likelihood estimators exist in all situations? When they do exist, are maximum likelihood estimators unique? The answers may surprise you. There are situations where an MLE does not exist. There are also situations where more than one MLE exists. And so what do we do in those situations? It's outside the scope of this course to get into the conditions under which MLEs exist and are unique. I mention this only to make you aware of the possibility of their non-existence or non-uniqueness. In the situations and the data sets we consider in this course, the MLEs will exist and they will be unique. As stated previously, the parameter space of the univariate normal distribution contains an infinite number of points. In fact, the number of points is uncountably infinite. How can we hope to find a point that maximizes the likelihood function in such a large set? That would seem to be like trying to find a needle in a haystack. In some situations, it is possible to derive formulas for the maximum likelihood estimators. In many other situations, maximum likelihood estimators can only be mathematically approximated using computational iterative techniques. For the univariate normal distribution, it is possible to derive formulas for the maximum likelihood parameter estimators. We use calculus to come up with constraint equations that the estimators must satisfy, and then we use algebra in conjunction with these constraint equations to obtain formulas for the estimators. Now the likelihood function was denoted by uppercase L. The natural log of the likelihood function, called the log likelihood, is denoted by lowercase l, and the expression for the log likelihood is shown here. Now, as a reminder, in this course, the notation log always represents the natural logarithm. Since the logarithm is a strictly increasing function, the values of mu sub x and sigma squared sub x that maximize the log likelihood function also maximize the likelihood function. One way to derive formulas for the MLEs is to differentiate the log likelihood function with respect to each of mu sub x and sigma squared sub x, set the derivatives equal to 0, and then solve the resulting system of equations for mu sub x and sigma squared sub x. The partial derivative of the log likelihood function with respect to mu sub x is equal to the following expression: the sum I going from 1 to n of the ratio of the difference between x sub I and mu sub x divided by sigma squared sub x. The partial derivative with respect to sigma squared sub x is equal to the expression the negative of the sample size over twice the variance plus 1 over twice the square of the variance times the sum I going from 1 to n of the square of the difference between each x sub I and the mean mu sub x. Setting these derivatives equal to 0 and denoting the MLEs using tilde notation, so mu tilde x and sigma tilde squared sub x, we get the system of equations shown here. This system of equations represents constraints that the MLEs must satisfy. We can then solve this system for the MLEs. Solving the system for mu tilde x and sigma tilde squared sub x gives the maximum likelihood estimators of mu sub x and sigma squared sub x. Specifically, the MLE of mu sub x is equal to 1 over n times the sum I going from 1 to n of the x's, and that's just the sample mean, isn't it? The MLE of sigma squared sub x is equal to 1 over n times the sum I going from 1 to n of the square of x sub I minus mu tilde sub x. This is the version of the sample variance with n rather than n minus 1 in the denominator. We now have preliminary estimators for the parameters of the univariate normal distribution. Unless there is a compelling reason to do otherwise, in general, we prefer to use estimators that are unbiased. That is, estimators that neither underestimate on average nor overestimate on average the parameters they estimate. We next evaluate these estimators from the standpoint of bias and make adjustments where necessary to obtain estimators that are unbiased. It can be shown that the expected value of mu tilde x, that is the mean of the sampling distribution of mu tilde x, is equal to mu sub x itself, and this implies that the MLE mu tilde sub x is unbiased as an estimator of mu sub x. On average, it neither underestimates nor overestimates the true value of the parameter mu sub x. Since mu tilde sub x is an unbiased estimator of mu sub x, it is standard to denote it using hat notation, and so we're going to denote it mu hat sub x. On the other hand, the expected value of sigma tilde squared sub x, that is the mean of its sampling distribution, is equal to n minus 1 over n times sigma squared sub x, which is strictly less than sigma squared sub x. And so sigma tilde squared sub x is biased as an estimator of sigma squared sub x. In particular, the MLE sigma tilde squared sub x tends to underestimate sigma squared sub x. Because of this, we usually use the bias-adjusted version of the estimator, which is the usual sample variance. We denote the bias-adjusted version as sigma hat squared sub x, and we can obtain this from the MLE by multiplying the MLE by n over n minus 1. And so when we do that, we get 1 over n minus 1 times the sum I going from 1 to n of the square of the difference between each x sub I and the MLE of the mean mu hat sub x. And again, this is the usual sample variance that we're used to from our previous statistics courses. In this next major section, We take what we've learned thus far and apply it to the process for deriving estimators of the parameters of the multivariate normal distribution. The starting point for our derivations is the likelihood function, which we will now define and construct. Let bold x1, bold x2, and so forth up to bold xn be a random sample of size n from the multivariate normal distribution of rank p with mean vector u sub x and covariance matrix cap sig sub x. For each I going from 1 up to n, the joint PDF of the components of the ith random vector bold x sub I is denoted by lowercase f subscripted with I, and with an expression shown here on the right-hand side of the equality, and we can write it in a couple different ways as shown here. Since bold x1, bold x2, and so forth up to bold xn is a random sample, the random vectors are stochastically independent. The joint PDF of the random vectors comprising the random sample is therefore equal to the product of their individual marginal PDFs. And so we denote the joint PDF of the sample of vectors by lowercase f, and it is equal to the product of the individual marginal PDFs. And so when we carry out that multiplication process, we get the expression shown at the bottom of the slide. So this is the joint PDF of the sample of random vectors. Now again, if the random vectors were not stochastically independent, then this equality would not be true. Because of this, independence of the random vectors is crucial. If they are not independent, then nothing that follows is applicable, because everything that follows is based upon this construction of the joint PDF, which depends on independence. Now, as before, the likelihood function is the joint PDF, considered as a function of the mean vector mu sub x and the covariance matrix cap sig sub x, given fixed values of the data. We denote the likelihood function again using uppercase L, and so it's equal to the joint PDF. Recall that the parameter space of the multivariate normal distribution of rank P is the set of all ordered pairs where the first coordinate can be any point in p-dimensional Euclidean space, and the second coordinate is a p by p positive definite matrix. Before we dive into the mathematical details of the derivation process, let's talk about the conceptual idea underlying maximum likelihood estimation for the multivariate normal distribution. If there is a point in the parameter space such that the likelihood function at that point is greater than or equal to the value it takes on at every other point in the parameter space, then that point at which it attains its maximum is called a maximum likelihood estimator of the true parameter point. As was the case for the univariate normal distribution, for the multivariate normal distribution, it's possible to derive formulas for the maximum likelihood parameter estimators. We use calculus to come up with constraint equations that the estimators must satisfy, and then we use algebra in conjunction with these constraint equations to obtain formulas for the estimators. To find a maximum likelihood estimators of the parameters, we must find a point in the parameter space at which the likelihood function is maximized. Now recall from college algebra the property of the logarithm function that tells us that when we take the log of an expression involving a product of terms, the resulting expression is the sum of the logs of the terms in the original product. The likelihood function involves the product of a number of terms. The log of the likelihood, on the other hand, is the sum of the logs of the terms in the likelihood. Maximizing a function involving sums is much easier than maximizing a function involving products, so maximizing the log likelihood function is much easier than maximizing the likelihood function. Because of this, we usually maximize the log likelihood rather than the likelihood. But what good does this do? Note that because the logarithm function is strictly increasing, points at which the log likelihood is maximized are the same as the points at which the likelihood function is maximized. So if we can find where the log likelihood is maximized, we've also found where the likelihood function itself is maximized. One way to find maximum likelihood estimators in this situation is to differentiate the log likelihood with respect to each of the mean vector, u sub x, and the covariance matrix, cap sig sub x, set the derivatives equal to the zero matrix of appropriate dimension, and then solve the resulting system of matrix equations for u sub x and cap sig sub x. The calculations in the multivariate case are more complicated than they are in the univariate case, and so they're not going to be shown here, but conceptually, the overall idea is the same as it is in the univariate case. The formulas for the maximum likelihood estimators of u sub x and cap sig sub x that are given on the next slide were found using this approach. The maximum likelihood estimator of mu sub x, which is denoted by mu tilde sub x, is equal to 1 over n times the sum, I going from 1 to n, of the x sub I data vectors. This is the sample mean vector. The maximum likelihood estimator of cap sig sub x, which is denoted by cap sig tilde sub x, is given by the two expressions shown here. Next, we evaluate these maximum likelihood estimators from the standpoint of bias and make adjustments where necessary to obtain estimators that are unbiased. It can be shown that the maximum likelihood estimator, mu tilde sub x, is an unbiased estimator of the mean vector, mu sub x. Because of this, as in the univariate case, it is standard to denote this unbiased estimator using hat notation, mu hat sub x. On the other hand, it can be shown that cap sig tilde sub x is biased as an estimator of cap sig sub x. In particular, the entries in cap sig tilde sub x tend to be attenuated towards 0. Because the MLE of the population covariance matrix is biased, it is typically not used as an estimator. Instead, it is adjusted to correct for the bias, and the resulting adjusted estimator is then used. Recall that the individual estimators comprising the MLE matrix, its individual entries, are biased towards 0. The bias-corrected version is obtained from this biased MLE by multiplying it by the adjustment factor n over n minus 1, which is slightly larger than 1. Doing this pushes the individual estimators within the matrix a little further away from 0, and this results in an unbiased estimator of the population covariance matrix. This unbiased estimator is often called the sample covariance matrix. Because it's unbiased, the sample covariance matrix is denoted using hat notation, so cap sig hat sub x, and the formula for its calculation is shown here on the bottom of the slide. Finally, let's look at a couple ways of constructing the various structures containing the parameter estimators that we've derived for the multivariate normal distribution. The formulas given above for the unbiased estimators, mu hat sub x and cap sig hat sub x, are matrix expressions that follow from the derivations. If one has access to matrix manipulation software, then these formulas can be used for calculation. But if calculations must be done by hand, then these formulas are of limited usefulness for computational purposes. The good news is that these estimators can be constructed by calculating each of their elements individually and then putting these elements together in their appropriate places in the estimated mean vector and covariance matrix. This approach is helpful when we don't have access to matrix software and we have to do the calculations by hand, say with a hand calculator. The next several slides show how to do the individual calculations and use them to construct mu hat sub x and cap sig hat sub x. Notice on the left-hand side, we have the sample mean vector, mu hat sub x. On the right-hand side, we have the vector of sample means. The MLE of the population mean vector has the sample means of the individual variables as its individual components. These individual sample means are easily calculated by hand, and once that is done, they can be assembled into the sample mean vector if the vector is actually needed. The individual elements of cap sig hat sub x are denoted by the following. So the ijth entry in that matrix is denoted by lowercase sigma hat sub ij. Formulas for the individual elements of this matrix are given on the next two slides. Let's first look at the diagonal elements in that matrix. The ith diagonal element of cap sig hat sub x is given by lowercase sigma hat sub ii. That is the estimated covariance of x sub I with itself, and that in turn is the estimated variance of the ith variable. And so this is the sample variance of the ith response variable. The off-diagonal element in row I and column j of cap sig hat sub x is denoted by lowercase sigma sub ij, which is the estimated covariance of the ith and jth response variables, and is given by both of the formulas shown here. This is the sample covariance of the ith and jth response variables. Once calculated, the sample variances from the previous slide and the sample covariances shown here can be inserted into their proper locations in a P by P matrix, giving cap sig hat sub x the estimator of the covariance matrix cap sig sub x. Let's summarize what we've done. We first derived the MLEs of the parameters of the univariate normal distribution, a distribution that we're familiar with from our previous statistics courses. To do this, we defined and constructed a likelihood function. We then discussed the big idea underlying maximum likelihood estimation. We provided a complete derivation of the maximum likelihood estimators by taking partial derivatives of the log likelihood function with respect to the mean and also with respect to the variance, and then solve the resulting system of equations for the MLEs. We then bias adjusted the MLE of the variance to obtain a variance estimator that was unbiased. We then derived the MLEs of the parameters of the multivariate normal distribution. Again, we defined and constructed the likelihood function. We discussed the idea underlying maximum likelihood estimation for the multivariate normal. And then, in analogy with the univariate case, we described the process for deriving the maximum likelihood estimators by taking the partial derivative of the log likelihood function with respect to the mean vector and with respect to the covariance matrix. The MLEs were then presented. And finally, we bias adjusted the MLE of the covariance matrix to obtain an estimator of the covariance matrix that was unbiased. So we've done a lot. I'll see you in the next lecture video.